So what we're going to do now is we're going to start talking about vector. And a vector is a dynamic array that can grow and shrink at the end efficiently. And what it does is it provides allocation that's dynamic. You can pre-allocate stuff. You can have it automatically reallocate when necessary. It supports highly efficient indexed storage, which is just the way a good old regular C++ or C built-in array works. And it also supports various methods that work efficiently on the representation of the vector, such as pushback and popback. And then there's also newer variants such as emplaceback as well. The vector abstraction supports so-called random access iterators. And as we'll see, random access iterators mimic the ability to be able to go to arbitrary locations or arbitrary subscript locations in the vector, just like you can go to arbitrary subscript locations in a built-in array. So in a sense, you can think of a vector as being very similar to, but ultimately a lot more powerful and safe to use than built-in C and C++ arrays. If you look on the right-hand side, you can see what the vector's interface looks like. It's got two parameters, type name t, which of course is the vector, the type of the vector, and then it's also got an allocator. And the allocator is used to dictate where the storage comes from to actually store the contents of the vector. And by default, there's an allocator out of the box called allocator. It's a very imaginative name. And the allocator that comes out of the box uses the operator new and delete. So it uses essentially the global free store operations to allocate the memory from the global free store and put it back to the global free store. But if you need to, you can take control over where the memory comes from. We're not going to spend a lot of time talking about that here, but it's something that you'll see is covered in later parts of the course. Okay, so now what we're going to do is we're going to go ahead and talk about and look at some examples of C++ vector containers. And that will be found here in this subfolder in my C++ GitHub repository. So we're going to start out by talking about vector. We've already mentioned this, so I'll go through this quickly just for sake of completeness. You can read the comments here if you forget what a vector does. I have a feeling you can probably figure this out since it's pretty straightforward. So a vector is basically a dynamically sized array that shields you from a lot of the dark corners and sharp edges of C and C++ built-in arrays. And one of the things that makes it better is, number one, it's got a whole bunch more operations. And number two, it also does storage management automatically. So you don't have to be responsible for calling new and delete. If you recall, one of the great C++ guidelines these days is don't call new and delete directly if you can possibly avoid it. Now, I realize in our programming assignments, periodically you have to call new and delete. But if you take a look at what you're developing in the programming assignments, it's abstractions that reduce the number of times you have to call new and delete or manage the memory for you more effectively. So the idea is to build abstractions that eliminate the need to call new and delete or minimize the need to call new and delete. Vectors are particularly efficient to access individual elements by their index, by their position. They're also useful to be able to iterate through in any order, including random access order. And you can also add and remove elements from the end of the vector efficiently. Okay, now under the hood, of course, you know that nothing comes entirely for free. So a vector takes up a little bit more space than a built-in array, but honestly, it's like an additional size field. So it's not really going to penalize you very much in practice. So you can, one of the cool things that vectors will do for you is as you're adding elements to them by using pushback or in place, they will automatically detect when they're running out of space and they will magically reallocate themselves under the hood. So as you go and add elements to a vector, it'll grow itself transparently so that there'll always be enough storage and you don't have to manage that memory directly. If you know in advance the max size that you'll need for your vector, you can reserve it or indicate it in the constructor and it'll pre-allocate it for you. All right, we've already talked about the signature for this thing, and let's go ahead and take a look at some examples that use C++ vector. This example first shows how to do the same equivalent code using a built-in C style array, and then we go ahead and show how you can do the same thing with a vector. So here's the built-in array. You can see we define ourselves an array of 3 elements, which will start out being uninitialized, and then we set array sub 0 to 7, array sub 1 to a sub 0 plus 3, and array sub 2 to a sub 0 plus a sub 1. So you can see here how we're able to use indexing into the built-in array in order to be able to read and write its values. You'll also notice, by the way, that you can use the subscript operation on a built-in array on either the left-hand side or the right-hand side of the assignment operation. So that makes it both an L value and an R value. What we do now is we go ahead and we print all the elements in our array one at a time for I equals 0, I equal to the end of the array, and we go ahead and print it out by using the subscript operation. So that should look very familiar. I hope you've had a chance at some point along the way to implement a C-style array in C++ just to see how it works. Now let's go ahead and take a look at the equivalent capability using a C++ vector, which is a sequential container. As with the built-in array, we started out by giving it the value of 3, so it has 3 elements. And then just identically to what we do up here, you can see we say v sub 0 equals 7, v sub 1 equals v sub 0 plus 3, and so on. So syntactically, the code is identical to the way in which we did the built-in array. And I wanted to kind of emphasize that just so you can see it works identically. And then we have a for loop, which is very similar to the one up here. The difference is that a vector keeps track of how many elements are in it, whereas a built-in array requires us to keep track of that information separately, which is what we do here, which is kind of ugly. So the nice thing about the C++ vector is it knows how big it is, and so we can write code like this, and it'll figure out the size, and you don't have to keep track of it. Now, you'll also notice something else here. I wrote the code as I did it here just because I was trying to mimic the built-in array syntax as much as possible. But you'll notice that this for keyword is highlighted by the IDE, and that indicates that it wants to give you a suggestion on how to do it better. And you can see what it says here is it says, use a range-based for loop instead. And the cool part is if you click on this, it'll magically convert your index-based for loop into a range-based for loop. And I'll try to use range-based for loops a lot because they're way, way, way better. And the reason they're way better is, number one, they're more concise, and number two, you never have to worry about an off by 1 fence post error again, because they keep track of all the information in the compiler and you can ignore it. So I'll talk more about the syntax later, but I just wanted to show you how you can convert from index-based loops to range-based for loops, usually by the click of a button in your IDE. So keep an eye on that when you're writing your code, and sometimes you'll get some good suggestions on how to improve things. All right, so now what I'm going to do is show you another way to access the vector. Now keep in mind, this does not have an equivalent, or at least not a direct equivalent, in the world of built-in C and C++ arrays. So what we're going to do is we're first going to resize our vector to be 0. So that means it's going to kind of ignore everything that was already there. It may keep the memory allocated, but it'll just move back the pointer to where the next item is going to go. And now what we're going to do is we're going to write a for loop that goes for I equals 0, I less than 7. And every time through the loop, we're going to increment by 1. And we're going to go ahead and call the pushback operation. And pushback will go ahead and take each of those elements, 0 through 6, and add them efficiently at the end of the vector. And remember that vectors allow efficient insertion and removal at the ends. And that's just by the nature of how they're implemented. So pushback is going to go ahead and add that at the end. And then what we're going to do here is we're going to go ahead and use our range-based for loop to print the contents. And you can see what it does is it says for int I, and I guess if I'm really being cool, I should say auto, for auto I colon v, that says for every element in vector v, go ahead and write out that element. So let's run this code and see what we get as results. Hopefully not too surprising. So you can see the initial results for both the built-in vector and the built-in array and the vector are 7, 10, and 17. No real surprise there. And then down here, we go ahead and push 0 through 6 into the vector by using pushback, and then we can print the values out using the range-based for loop. All right, so this is kind of vector 101, right? Not too complicated, mimics a lot of what's in an array, but much cleaner, can be resized, will manage the memory automatically, lots of other operations that you don't get out of the box with a built-in C and C++ array. And I'll also mention this just very briefly, for these types of data structures, these types like an int or a double, it doesn't really matter how we put it at the end of the vector. There's also another mechanism called emplaceback. And for data types that have more complex constructors and assignment operators than an int does, you're often better off using emplaceback rather than pushback. And in fact, you'll see that the CLion IDE will basically give you a hint that says prefer emplaceback when it matters, which is pretty cool. We'll talk more about that as we get further along. That was 3A. Let's go look at 3B. This particular example is just a minor refinement to what we looked at before. And the main contribution it makes is it just shows how trivial it is to change from a vector of one type, like int, to a vector of another type, like double. So in this case, we define ourselves a vector of double. We put some elements into the vector. We push them at the end. We go ahead and do some operations that use the subscript operation on the left-hand side and the right-hand side. And then we go ahead and print the results out using a range-based for loop and the auto keyword. Now, again, I can run this code for you. I can assure you that it's pretty mindlessly easy to understand. And we did basically get the results of doing those pushback operations followed by the operations that will store into location 0 and 1. So nothing particularly profound with this example other than showing how easy it is to switch between different data types. And of course, that's one of the key themes in C++ STL is how you can parameterize the containers with different type keys. In this case, double versus int. Okay, the next example we're going to look at here shows vectors being created using C-style arrays and character pointers, as well as using the more modern C++ initializer list semantics. So let's take a look at this example. This also gives you a feel for how things used to work in the early days of C++ and how much they improved with later versions of the C++ standard. So here we're going to define ourselves a built-in array of ints with a bunch of ints in them. And then we're going to define ourselves a vector of int, and we're going to give it the address of the built-in array, and then we're going to give it the address of the built-in array plus the number of elements in the built-in array, which I can also get by saying size of AR divided by size of star AR, which I think I like a little bit better. And so what that'll do is that'll use the constructor of vector that takes two iterators, one to the beginning and one past the end, and copies the contents of that built-in array into the vector. So that's kind of the old school way of doing it. That's the way you had to do it in the beginning. With more recent versions of C++, starting, I believe, in C++ 11, you could use an initializer list. And there's a couple different variants of this. One approach looks like this, where you have basically a constructor with the initializer list inside the constructor. And the other variant says, why do we have these extra parens? That's kind of pointless. Let's just give it an initializer list. Both approaches work. And you can see in this case, we're just initializing the vector from the initializer list. We then go ahead and use a range-based for loop to print the contents out. Down here, we show similar construct, except this time we're going to make a const char star that has the string literal hello world. And then we go ahead and we create vec3, which is a vector of character, by giving it stir and stir plus stirlen. So it's going to go ahead and copy the contents into that vector v3 or vec3. And then just for kicks, we also show how you can create another vector where you explicitly spell out each of the characters. So we can do the same thing, except now we're doing it with character by character initializer list to get the same result as using the string. And then we go ahead and print the results out using the range-based for loop. So let's go ahead and run this code, and it prints out what you'd expect. It prints out hello world. So this is just showing how you can initialize the various vector containers using initializer lists, using built-in arrays, and so on and so forth.